to speak in Portuguese if nobody is opposed to this. But anyway, Ricardo Matheus is our vice director. And he finished his PhD in USP. After that, he did a postdoc at USP. Then he was immediately hired at Unifesp. And then he smartly moved to IFT. So thank you very much, Ricardo. You are very well known for the good lectures you give. So I hope to learn something today. Please.
Okay, thank you, Jorge, for the kind introduction. Is there anyone that does not understand Portuguese here? Because he asked me to do it in Portuguese, but I can do English there. So then I'll continue in English, right? So I hope I can live up to the expectations of Jorge. And the idea today is to talk about opportunities and challenges, so essentially the future of particle physics, right? And it's important to know that also in the title is a personal view. And that is there because when you're talking about the future, it's very, very important to not have to be right. Right? So that's the disclaimer here. It's just a guess, but it is my best guess. And I hope I can get at least in the ballpark of the target, right? So the standard model of particle physics is well known, right? It's composed by these degrees of freedom right there and these symmetries, right? That's essentially the combination of these two ideas, right? What degrees of freedom are there in nature and what symmetries they respect. That allows us to build a Lagrangian, and everything else is just a consequence of that, right? It is a model that works. It works really well, right? And the reason for that is that this symmetry, and in particular the symmetric breaking pattern, together with this choice or this fit, right? This is guided by experiments, right? But these degrees of freedom make a lot of non-trivial predictions, right? What do I mean by that? I mean that when you build a Lagrangian out of these two ideas, right, that Lagrangian has a lot of operators. This is just a small piece. When you really expand the Lagrangian for the standard model, there's a lot of operators, right? But not that many parameters, right? So this is, you can see right here, the sector where the interactions between the bosons, right? W Higgs and Z W Higgs. But the coefficients in front of these operators are all controlled by very few constants, actually. So the model is super predictive, right? You could, in principle, measure all of these operators separately, right? And test against other operators. So in total, we have 19 parameters in the standard model. And these are a particular basis, right? You have some freedom of choice on how to choose these parameters, of course, right? But this is a particular base with the 19 parameters that you can see here, right? So the masses of all the fermions, some mixing angles, complex phase, 3-gauge couplings, CP violating term, and the two parameters that control the potential of the Higgs. It's a very important thing to realize here that out of these 19 parameters, right, 15 are directly related to Higgs physics, right? So you have these two parameters that fix the Higgs potential, essentially fixing the quadratic and the quartic part of the Higgs potential. And all these in red are essentially the same as choosing Yukawa couplings with the Higgs, right? And so understanding, that's the first takeaway message from this talk, is that really understanding the standard model means understanding Higgs physics, essentially. The 3-gauge couplings we kind of understand well, right? The Higgs physics is way more complicated than the rest. And as an aside...
Ricardo, right? Question.
Yeah.
What about the mass of the neutrinos?
Yeah, it's here, right? I was about to say, right? So this as an aside, right? The standard model does not include massive neutrinos, right? We don't know where the mass of the neutrinos come from, But the simplest choice would be, I mean, the simplest from the theoretical point of view, would be to assume it's the same as the others, and there would be 7 more parameters, essentially, again, Yukawa couplings. Right? If the neutrinos get a mass just like the other fermions, right? I'll give more details when I get to neutrinos later. Right? So again, 3 masses, 3 mixing angles, and 1 complex phase. Right? That's why 7. So, and that's it, right? Essentially, you have a lot of the standard model, right, controlled by the Higgs interactions, right, with itself and with the fermions. Right? So, what about tests, right? Let's see what we're doing today in particle physics before we go to the future, right? The last batch of news from the accelerators, right, essentially refer to these couplings with the Higgs, right, that I just mentioned. So here you can see this red line is the standard model prediction, right? Why do you have a prediction? Because in the standard model, all fermions get masses from the Higgs, right? And that means that the coupling with the Higgs should be correlated with the mass of the particle. So you have this straight line right there. You have the mass here and the coupling of the Higgs essentially on the horizontal axis. And we have tested all of these, right? They are very close to the standard model prediction, right? So full agreement so far, right? And it gets harder and harder to go down here because the lighter the particle, the smaller the coupling with the Higgs, and at some point you don't have enough luminosity to test it, right? And so that's why the charm is still like a big error bar, right? Despite being a little heavier than the muon, but charm is way more dirty measurement in terms of backgrounds, right? Because there's a lot of QCD involved. But we have been testing as far as we can, right? So the lightest particles are untested, right? And will remain untested as far as the LHC is concerned, right? We will never get that far below the muon Yukawa with the present day accelerators. Right? Same for the neutrinos, right? In the case of the neutrinos, there's not even a standard model prediction because we don't know how neutrinos get masses. And I'll get more details about that in a second. Right? This is another similar plot, this one from CMS. Right? These 2 axes are basically fudge factors. Right? These kappa factors here are just multipliers. You could take the coupling of the Higgs with vectors. Right? The standard model is, by definition, 1, and you multiply by a factor to see how far it deviates from the standard model. And here is the coupling with fermions. Right? And you can see the standard model prediction is the 1, 1 point right there. Right? And this is the story as the CMS progressed, accumulating luminosity. So right at discovery, you had this red point. After the end of run 1, it was closer, and now this is all with all the run 2 data. Right? This is basically all the data we have right now is really close to the standard model prediction. Always within 2 sigma, right? So again, the coupling of the Higgs with fermions and bosons has been confirmed by the experiment so far. And this is a little more detail. Again, these are these fudge factors that should be 1 for the standard model. And here, instead of just saying vector, I'm specifying the vector. So this is the W, the Z, the photon, gluon. Here are the fermions, right? Top, bottom. And you see everything that we were able to measure is agreeing with the standard model so far, right? So this is the piece of news that is basically no news, right? We have been confirming the standard model so far to bigger and bigger precision, right? You see that some of these measurements are getting really precise at this point, right? One part that is completely untested so far is the Higgs couplings with itself, right? The Higgs potential is something that we still didn't test, right? Under the assumption that the standard model is correct, measuring the mass of the Higgs allows you to get the parameters for the potential, right? But that's under the assumption that the standard model is correct. You have to test it directly, right? So here is how well we can test so far the trilinear Higgs coupling, right? So this lambda here, again, is a fudge factor. So 1 here should be the standard model, and the rest is just a multiplicative factor for that coupling. Right? And you can see with present day data, is this solid black line here, we can exclude the trilinear coupling like 7 times bigger than the standard model in the positive direction, like -1 in the negative direction. But we didn't get to the point, if you bring this black line down here, this is the prediction for the standard model, right? So you have to bring it like a factor 3 down to actually be able to directly observe the Higgs coupling, right? This vertex. And we are not there yet, right? And we cannot do it with the LHC in this present configuration. I'll talk about the high luminosity LHC at the end. So that's the situation nowadays, right? The key point that all particle physicists keep hammering on again and again is that despite all this success, the standard model is not finalized, right? We're sure we don't have a final theory of particle physics, right? Because there are many missing pieces, right? The key one, which is straight away coming from experiment, right, is the neutrino masses, of course, right? There's no neutrino masses in the standard model. Experiment tells us neutrino have masses, so you have to do something about it, right? So for all the fermions in the standard model, right, the masses are just obtained in this way, right? This is the VEV of the Higgs. So it's a Yukawa coupling, and when the Higgs gets to its VEV, you get this constant, and this is a mass term, right? But we never observed, in order to write this, you need a right-handed particle, right, the neutrino, and we never observed a right-handed neutrino. We don't even know if that exists or not, right? So this was never included in the standard model, right? A key point that was made in the talk last week, right, was that obligatorily, if you want to go from massless fermions to a massive fermion, you need extra degrees of freedom, right? So now that we want neutrinos to have masses, that is a direct conclusion that you have to include some new degree of freedom in the standard model. So you have to extend the standard model, at least in this very minimal way, right? So that's a given. So we have already observed, in that sense, we have already observed physics beyond the standard model, the neutrino masses, namely, right? So the bad solution for that, and here I want to be very concrete in what I mean by bad or good, right? Bad does not mean impossible. Bad does not mean improbable. Bad just means it's bad for us, right? In this sense, in the sense that nature, like that's why falling meteor, nature sometimes doesn't care about the dinosaurs, right? It's just is what it is, right? So the bad solution is bad because if that is what is implemented in nature, we'll probably never observe it. That's why it's bad, right? And you can see here, this bad solution is just you just postulate a right-handed neutrino, and you postulate there the neutrinos are Dirac fermions. These are two different things, actually, right? I'll tell why in a second. In that case, you just have to put a very small Yukawa for the neutrinos, order 10 to the minus 12, right? And then you have the neutrinos around here, right? Theoreticians don't like this because there's this big gap in the middle, right? Although there are big gaps here too, it's just the log plot, right, that hides this big hierarchy here on the right. But there is a bigger gap between the lightest fermion and then the neutrinos on the other side. So theoreticians like to look at this and say, oh, it's a completely different mechanism. But that's just something just argumentative, right? There's no actual proof of that. Right? So that could in principle be true, right? And the problem, the reason this is bad is because now these right-handed neutrinos that you put in, they don't have color, they don't have charge, they don't have isospin, no hypercharge, nothing, right? They have no interactions other than gravitation. and this is tiny, tiny Yukawa, right? This is way beyond anything we try to observe this far, right? You see, even lighter than the muon was hard, right? This is another 10 orders of magnitude, right? So it's just a solution that we see nothing, right? The only new thing that you actually postulating here is lepton number conservation, right? Because the moment you put a right-handed neutrino, right, you should also put in your Lagrangian a Majorana mass term for that right-handed neutrino. That is not forbidden by any other symmetry, right? So if you want Dirac neutrinos, you have to postulate, you have to elevate lepton number conservation, which is just an accidental symmetry in the standard model, to a postulate. Otherwise, these guys are not Dirac neutrinos, right? They will also have a mass term not forbidden by any, a Majorana mass term not forbidden by any symmetry. So there's two things you need to do for this solution. Postulate lepton number conservation and introduce this right-handed neutrino. Right? Of course, there are many good solutions. And again, good doesn't mean more probable, doesn't mean the one I'm betting on, right? It just means that solutions that actually can be tested in the near future. Right? That's what good means. And that's why I use this symbol every time I'm talking about good solutions. Right? I'm just talking about this anecdote that you should look where you can find stuff. Right? And that's all there is to it. Right? You're just, these are just solutions to the neutrino mass problems that make predictions that can be tested in some way or another in experiments that are either already working or in planning stage, near future, in the next 20 years, right? So there are a bunch of possibilities, right? You could take masses from a different scalar than the Higgs. You could have extra dimensions, many types of seesaw, right? All imply Majorana fermions, right? And that's the actual poster boy of neutrino mass model, right? It's the model that everyone likes and prefers, which is giving Majorana mass for the neutrinos. Right? The simplest way you could do that is you forget the right-handed neutrinos, right? Don't need them, right? Just keep the left-handed ones and write an effective operator for them, right? So this is already probing some new physics at some high scale, some high UV scale that's generating this dimension 5 operator, right? Composed only of left-handed fermions, and the Higgs, right? When the Higgs gets a VEV, this is a Majorana term, right? And the main prediction here is the opposite of the previous one, right? Is that lepton number is not conserved, right? So neutrinos actually can annihilate antineutrinos, right? So lepton number is not conserved, right? They are their own antiparticle, right? And that allows for this very particular decay. So you see a beta decay here, right? A neutron decay into a proton emits an electron and a neutrino, right? But if the neutrino is its own antiparticle, right? The neutrino emitted by one beta decay can annihilate another simultaneous beta decay, right? And you have this double beta decay without any neutrinos, so-called neutrino-less double beta decay. Right? And you can look for this. Right? This should be a very rare event, but rare events can be offset by having a lot of particles. Right? So you can increase the volume of some radioactive material that does this decay, and if you increase that volume enough, eventually you see this. And there's a lot of experiments doing that. Right? This is current day expectations for these experiments, right? So I won't go into details here, but there's two ways you can explain the observed neutrino oscillations, right? There's a normal ordering for the mass of the neutrinos, and this inverted ordering, right? Normal means that the first generations, right? The mass that gets more contribution from the electron is the lightest, like in the rest of the standard model, right? The first generation is overall lighter than the second one and the third, so that we call that the normal one, and the inverted one is the opposite, right? And this is the reach for the next generation of experiments on double beta decays, looking for the double beta decays, right? So it could be lucky, and if nature chooses this option, we might be able to see double beta decays in the near future and then know that neutrinos are Majorana particles. If we are unlucky, then we don't see anything in these experiments. We will have excluded this guy, right? And then it all depends what happens in the oscillation experiments, because we're also doing neutrino oscillation experiments that I'm not mentioning here, but that might be able to measure these masses. And then suppose they conclude it is the inverted one, but the neutrino-less double beta decay gets here and finds nothing. Then that would mean they are actual Dirac particles, right? And this is the experiments actually, and you can see that these ones are already taking data, right? And these are planned future experiments, all of them looking for neutrino-less double beta decay. If you look at the bottom of these two, right, and the scale there, we'll start touching the normal ordering on the upper limit here with those experiments, right? But they are all in planning stage. There's not even a schedule for those yet. So it's hard to know when they get there. The main message here is that we can get answers by doing these experiments, but we are not guaranteed to get answers, right? The bad solution is always there. And if the bad solution is realized in nature, we'll see nothing, right? But we still have to look, right? That's the main point. If you don't look, you'll never know, right? You might get lucky, find something. You might get unlucky and not find something. That's the honest assessment, right, about the situation. All of them, nuclear, you just essentially put a nuclear material somewhere, surrounded with detectors and wait, right? And the rest is just trying to get a pure enough material. No, they do, right? I mean, I don't know the details of the experiments, right? The experts on the subject think they are good experiments in the sense that they are actually putting limits. Oh, the theory.
Yeah, all these experiments are related to nuclear physics. A matrix element, double beta decay, and so you need nuclear structure calculations. And this is a strongly interacting many-body problem, far from trivial. And
no. I understand what you're saying. I don't know the answer to it. I never looked into the theoretical modeling. Of course, once you don't see double beta decays, you have to roll that back to the neutrino mass using theory, right? And that's not trivial, I agree, but I don't know. I don't know what kind of effect could be important there. I really don't know. Okay. So now, next unfinalized aspect of the standard model, right? Dark matter. That's another observation we have, again, experimental data, that there is something out there, there is fiddling with rotation curves of galaxies, doing bullet clusters and all of these things that we don't understand. We see there's something doing gravitational interactions, but we don't know what it is, right? Is that a problem for the standard model, right? And you can argue that probably yes, right? Because another thing that it could be is modified gravity, right? In my opinion, again, this is personal opinion, right? The kind of observation that really makes it difficult for modified gravity are things like that. This is called the bullet cluster, right? There are more than one observation of this kind. And what you see here in red is X-ray, what you would see if you were looking at these guys in X-rays, right? This is essentially X-rays emitted by the gas there that got hot because there were two clusters of galaxies that collided here, and this guy came from the right, this one came from the left, and they crossed each other, right? And this is where most of the mass is where this superheated gas is, right? the blue thing is where the gravitational well is, as observed by lensing, right? So when you look at the galaxies behind these, you can see that there is a big gravitational lens here, right? There is deviating radiation, so you know that the potential well is here, but the mass is there, right? This is kind of tricky for modified gravity, right? You have to figure out some kind of theory of gravity that decided to project the center of the gravitational well in the direction that things were moving. It's very hard, at least in my mind. If someone, I bet there are models out there that do that, but I don't want to hear too much about them because it gets way more complicated than just postulating some new component. Right? Another thing that it can be is compact objects, right? You could think, well, this is just made of the usual standard model particles that we know, really clumped down in small objects with high mass. Right? So dark matter would be something with very low number density, but in total you get... and the main candidate for that nowadays is this primordial black hole. So a lot of black holes generated at some very early period of the universe. And these are experimental constraints. So what you see in blue and gray here are regions that are excluded. Yellow means future reach of a projection for future experiments, right? And this vertical line here is the percentage of dark matter that could be made of primordial black holes. So this upper limit here is 100% of all dark matter is primordial black holes. Of course, you can play this game of having all the solutions together, right? You can have a little bit of the dark matter be primordial black holes, a little bit modified gravity, a little bit is particle physics, but then you're putting more and more parameters, right? At some point, you fit anything, right? Yeah, but if you go with the pure primordial black hole, that's not strictly excluded yet, right? You see there's a point there that you could, in principle, have 100% primordial black holes. The problem then is in theory, right? That is beyond my expertise, but I understand that it's still not clear if you could actually produce that many primordial black holes to actually fit the bill here. Right? But from experiment, still allowed. And then it could be particle physics. Right? If it is particle physics, right, what is the problem? Right? The problem is that we have to go into the standard model and look for someone that could be dark matter. Right? The first constraint that it shouldn't have charge nor strong interactions, right? And that already excludes almost everyone. You are left with these 5 guys, the 3 neutrinos, the Z, and the Higgs, right? If you demand that there is a stable particle, right, that lives all through the story of the universe, then you exclude the Z and the Higgs because they decay almost promptly, right? And then there are a lot of constraints from cosmology that tell us that the dark matter should be cold. And that translates into a lower limit for the mass, right? Telling us that dark matter should be GeV, maybe keV heavy, right? Certainly not milli-electron volt, which is what we have for the neutrinos. And that excludes the neutrinos, right? And so we have no candidates for dark matter in the standard model, right? We have to augment the degrees of freedom. As usual, there's a bad solution. Now remember my definition of bad solution, right? And the bad solution here is that almost anything that is sufficiently weak coupled, and weak here means weaker than weak interactions, right? Can have, in the limit, right? The only interaction that we are sure dark matter has is gravitational interactions, right? So there's a huge space. This is a plot where you put the mass of your dark matter candidate particle, right? And here is the cross-section in centimeters, here is in picobarns, right? And this is kind of, on this ballpark, you're talking about weak interactions, right? But you could go down all the way, there's another 20 orders of magnitude here before you get to gravitational interactions, right? If dark matter is anything that lies down here, you never see it, or not in this foreseeable future that we're talking about. So again, you have a bad solution, it works, right? As far as I know, there's nothing that you could say that say this is impossible. It's perfectly possible, but not good for us, right? And these are present-day experiments. Now, the good solutions predict things that we can now actually observe, right? So you want this particle to be with masses that are close to what we can observe today, and interactions of this weak kind of interaction, maybe a little weaker than that, we can still see, right? And once you allow these dark matter particles to interact with the standard model, there are many different observations you can talk about. This is a very famous picture, right? And each direction here is a different observation. So you could collide two standard model particles to produce dark matter. That's what you do at particle accelerators, right? You could just make big detectors and wait for dark matter to bump against your atoms, right? That's the direct detection case. And you can look at the sky and wait for dark matter to annihilate into standard model particles and try to see those. And that's the indirect detection. All of these are possible. And I listed a bunch of different models, right, that could do all of those things, right? And what they have in common is that all of them, almost all of them, have at least one, if not two or three of these observation channels, right? So talking about direct detection, which is related to this original plot, this is the prospect for the next years, right? So this plot comes from Quanta Magazine, right? But you can see here different kinds of dark matter, classified here according to the mass, right? And the list of experiments that in principle could give us information about all these different kinds of dark matter, right? And this is the projection for the next few years of direct detection experiments, right? So you see, even the neutrino background that is mentioned a lot is not totally impenetrable, right? The neutrino background means that once you get to this blue line, the neutrinos coming from the sun become a serious background to our observations. You start seeing neutrinos. Right now, you're tuning your detectors so that the neutrinos interactions are too weak to excite your detector. But once you get here, you cannot do that anymore. You will actually have to model that background and subtract it. It will become much harder to see dark matter at that point, because now you have a huge background. But you see that the planned experiments can go a little bit inside. You see that shaded area here, right? But eventually, well, that's the prospect. And this is the list of experiments that represent this green part, the blue part. So the green ones are operating. And of course, this is, again, a matter of luminosity, which in this case is the integrated time you have your detector on, right? The longer you wait, the bigger the chance of seeing dark matter. And you put a constraint that moves down. And this is the present-day constraint. Right? So again, the message is the same, right? I will repeat this a lot, right? It is true that we can find, right? If the dark matter is somewhere here or there, we might still see a WIMP somewhere, right? But it's not obligatory, right? The bad solution might be the one nature chooses, right? And maybe we'll see nothing. But again, we'll only know if we look. So my point is that if you don't do experiments, you'll never know. And that's it for the neutrinos. There's a few other missing phenomena that I won't go into detail here, right? We know that there is more matter than antimatter in the universe, right? The standard model cannot take care of that. It's missing. It doesn't do enough CP violation. And you also need some out of equilibrium process to do that. So you would have to have a first order phase transition in the standard model as you break electric symmetry, and it's not, it's a crossover, right? If you look at the standard model we have today with the parameters we have, it's not a first order phase transition. So you need to solve that. There are models that solve that. The simplest one is just another Higgs doublet. Right? Just putting one extra Higgs doublet gives you a lot more CP violation and a strong transition. Putting more scalars usually increases the sharpness of phase transition. So That's a simple solution, but there are many others, right? Including some of that solve neutrino masses and dark matter, right? And there's also a big missing piece, but this one is way more distant from us nowadays, right? And again, the message for this first part is also that you could actually probe some of these extensions of the standard model and see something. You could see nothing, right? But in any case, you need experiments to know. This one is harder, right? This one, we don't know what experiments to do. So far, we cannot test that. Now, another point about the standard model is that the standard model is not also very well understood, right? There are many things in the standard model. There are not missing pieces, right? We're fitting the data pretty well, but we actually don't understand or suspect there's some deeper explanation behind just fitting the data, right? So one of them is, this is not something that would require changing the Lagrangian. We actually believe that the Lagrangian for QCD is what it should be, but it's more understanding how it generates confinement. That one I won't talk too much about. Gaston did it beautifully a while ago, so I advise you go there and look, right? So I'll focus on the weak part of the standard model, right? And in this part, one puzzling thing is the physics of flavor, right? Why the standard model has these 3 families, not 4? Why you have this increasing mass as you go from one family to the other, right? Also the mixing. These 2 drawings here represent the mixing between different families, right? And you see that in the quark sector, this is almost diagonal, right? The size of the square in the picture is proportional to the number that goes there squared, right? Which is the important parameter to see mixings, right? But in the neutrino sector, there's a huge mixing. We don't understand any of that, right? These are just numbers that we fit to experiment. It's all the Yukawa couplings that I mentioned before, right? All these parameters that, and there are proposals, right? Against some of the usual suspects are here, right? So warped excitation, partial compositeness, these are all also solve dark matter. They also solve many of the other problems, the neutrino masses, right? And they can contribute to the physics of flavor, right? Also, there are the fine-tunings of the standard model, right? This is the most polemic part, probably, right? Which are these numbers in the standard model that are way smaller than you would expect from the quantum corrections that they receive, right? So 2 of them are listed here. There's a strong CP problem and the cosmological constant. I won't say too much about these 2. This one is related to a parameter that I show at the start. It's a CP violating phase for QCD, right? Which is, as far as we know, 0 and should be big, right? And you could propose extra Peche-Queen symmetries to address that. Usually that implies a new particle called the axion or axion-like particles, right? Which are observable. And there's the cosmological constant problem, which is probably arising from the fact that we don't know how to treat QFT vacuum as well as we should, and that's a tougher theoretical problem, right? So these 2, again, fall under this same banner, right? We could, in principle, probe these guys, right? With the same experiments I'll mention here, but not necessarily we'll find answers, right? But the one I want to talk more on the fine-tuning is, of course, the hierarchy problem, because that was the whole hype behind the LHC, right? We talked a lot about this hierarchy problem before turning the LHC on, right? We're paying the price for that now, but let's see what we can learn about this one, right? So just to understand a little bit what hierarchy is, right? Let's take a look at the very simple toy model. So this is just a Lagrangian, right? Where I put one scalar and one fermion. That's it, right? And one Yukawa interaction between the scalar in green and the fermion in red. That's all, right? This is a 3-parameter Lagrangian, right? There's 2 masses, right? and one adimensional coupling Y. Right? And you could ask your question, right? If I look at low energies for this theory, right? In which part of this parameter space, of these three choices that I can make for these numbers, I have a light scalar and I don't see the fermion, right? Naively, you could say, well, I just have to take the little m, much smaller than the big M. This is the mass of the scalar. This is the mass of the fermion. And I'll get an effective theory at low energies that has a light scalar and nothing else. Right? But that's not actually true. Right? And you can see that very easily just by integrating out the fermion. Right? If you look at the contributions that the fermion has to the scalar propagator, you have to calculate this loop. Right? At one loop, that will be the contribution. Right? So you get this effective Lagrangian down here just by integrating out the fermion, right? There are interaction pieces that I don't care, right? But the propagator will come from this part. It's not properly normalized. But the point you can see here is the pole, right? The physical mass for the scalar is actually set by this expression here. This is the pole will be in this physical mass right here. Right? And notice, in this case, the cutoff for this theory is the mass, the big mass that I integrated out. When I get to that mass, I have to integrate in the fermion and look at the full theory again. Right? So from an effective field theory perspective, this is the mass of the scalar, right, at low energies. And if I want this mass to be much smaller than the fermion mass, so that it even makes sense to integrate out the fermion, right, I need this thing to be very small compared to the scale of these two guys, right? I actually need some relation between my ultraviolet parameters that forces the mass of the scalar down to, I don't know, many orders of magnitude before. The more orders of magnitude you want, the better this matching must be, right? And that's what we call fine-tuning. It's as simple as that. What you're saying is that the physics of the low energy theory depends a lot on the details of the ultraviolet theory, right? So fine-tuning UV sensitivity is the same thing in this case. Right? That's all there is to it, right? We understand this kind of relations very well if there is a symmetry that enforces it, right? But without a symmetry, this is not very stable under radiative corrections. You have to be more careful, right? You have to see what happens at two loops, etc. If there's a symmetry imposing it, it's fine. So this is what I just said, UV sensitivity, right? Nowadays, I see a lot of people trying to call these other names like UV, UR mixing, right? But what I want to make clear here is that this is not a breakdown of effective field theory. This is not a breakdown of quantum field theory. This is not a breakdown of reductionism, right? This is actually a prediction of the Wilsonian approach, right? That you have this kind of possibility. It's possible that this is happening, right? What is really breaking down here is something we like a lot in physics, which is separation of scales, right? It's very neat and convenient when I want to study an object and I don't have to care about the behavior of its very small constituents, nor what Alpha Centauri is doing, right? So I only have to do physics in the scales close to the object I'm looking at, right? What happens in these particular cases, if this fine-tuning happens, is that this breaks down. I will only understand really what's going on when I get to the UV, not before, because the whole physics is being set in the UV. Right? It's inconvenient, yes. It's not impossible. So the bad solution is already on the table, right? Well, the bottom line of this approach is that scalars are very sensitive to this. It's very hard to forbid couplings to scalars, right? This is invariant under all the symmetries that we know, right? And it's still a dimension 2 operator. So you could put a lot of things here and couple to the Higgs. It's hard to forbid this. Even if the Higgs has new charges that we don't know about, right? These will still be invariant under those new charges. So it's very hard to forbid, and that makes scalars really sensitive to any new physics at all these scales above the electroweak scale, right? So the reason we worry about this is that all these other solutions to the problems I already mentioned, right, will imply new scales for physics at some point here, right? The person that did this picture was not me, right? Decide to put just the gut scale and the Planck mass, but you could have other scales here where flavor is happening, where dark matter is happening, where you're generating a Majorana mass for neutrinos. All of these could generate scales here, right? And the Higgs would be really sensitive to those scales, right? So you need fine-tuning for those scales. And here I want to make a very important point, especially for the students. Notice I'm never talking about some artificial cutoff that you send to infinity when doing renormalization, and it's not physical at all, right? I'm talking about physical scales, actual particles that could be here, and theories that would have to be really fine-tuned to generate a light scalar. In heavily fine-tuned, right? So one of the hypotheses that people have worked on a lot, right, is the big desert hypothesis, which is there's nothing here, only the Planck scale, right? No new scales. In that case, the cutoff of the standard model will be the Planck mass, right? And since the story for the Higgs is exactly the same as the toy model I showed, this is the one loop contribution. This is the mass parameter. It's actually the potential parameter for the Higgs, the quadratic part, right? And these two things need to cancel each other, right? To generate something that is 10 to the 4th in here, so that when I take the square root, I get order 100 mass for the Higgs. And that means that that theory at the Planck scale should have cancellations between a few parameters that occur in one part in 10 to the 30. Right? So it's not just a small fine-tuning, it's a huge fine-tuning. Yeah? And that's kind of the bad solution, right? And then there's the LHC will solve it hypothesis, right? Also known as natural solution, right? Which is really looking under the lamp, which is if you put one TV here, right? Divide by 16 pi square, you get this 10 to the 4th, and then you need no fine-tuning. You have just cancellations between numbers which are of the same order of magnitude, generating another number also of this order of magnitude, right? But that would predict new physics at this cutoff, 1 TV, right? And we have been looking for that and didn't find anything, so it's not exactly. Supersymmetry is one of them. I'll mention in a second. But supersymmetry would predict this. Right? Some flavors of supersymmetry, right? There are many. Right? So this is putting serious constraints on models at this point, right? So already the bad solution is very clear, right? You could just say, well, it is what it is. These numbers just are fine-tuned, right? Nature could choose any number and choose these two very similar numbers, and we will never know until we get to the UV physics, right? No experiments will be able to test that in any foreseeable future, right? And the good solution actually predicts things, new physics at some low cutoff. So you have to bring the cutoff down, right? That's the composite idea. So if the Higgs is really composite object, right? Since we have never seen any fundamental scalars in nature, right? It's one of possibility that the Higgs is not fundamental. Then the cutoff is when you start seeing the internal structure of the Higgs. Another possibility is SUSY, as Gaston was mentioning, which you conceal the loop corrections. But in order to do that, the super partners need to be of the same mass as the standard model particles, and that's not the case. So there's a little breaking of SUSY, and the bigger that breaking is, the more you recover a fine-tuning, right? So you're pushing that into the fine-tuning region for both cases, right? And there are some cosmological history mechanisms, but it's not very clear if those are like relaxation models. It's not very clear that these are theoretically consistent yet, right? So I won't delve too much into this. Right? And The consequence of the LHC so far, that we didn't see no signs of new physics around 1 TeV, right, is already implying, pushing this cutoff to 5 to 10 TeV, right? This is a fine-tuning of order 1%. I just have to do the same calculation I did before, right? That means that numbers, if you find anything at 10 TeV, numbers will have to conceal at order 1%, right? That can still be arranged for, right? That's why there are models that have been proposed that predict only physics, that new physics at 10 TeV. All you have to do is suppress couplings to the Higgs at 2-loop level. Then you have a 16 pi square going around and you get that 1%. You could use a solution, in the case of composite Higgs models, you use a solution very similar to what the pion did in QCD, right? The pion is like a factor 6, 5 lighter than everyone else. In here, it would have to be a factor 10 lighter or a factor 100 lighter, right? But again, you're talking about some spontaneously explicit breaking of a spontaneously broken symmetry. You get this pseudo-Nambu-Goldson boson. Right? So you can still do those theories. They are less good-looking than the ones that predict physics at 1 TeV, but they're still around, right? The fine print of all this whole discussion is that most experimental exclusions that we have available, right, are done into simplified models. And simplified models can leave what we call blind directions, right? So you're looking for one particle and you don't find it. You look for another one and you don't find it. But there might be interference between those two if you make a full model. And if that interference is negative, your discriminating power is way less than you could expect from the simplified version, right? So, and in that sense, we're trying to correct that by doing more effective field theory. Now you're just looking for all the operators that could be generated at order at dimension 6 or 8 in the standard model, and putting constraint on that, because any physics that exists into some higher energy should contribute to these operators. So if you exclude the operators, you're doing a more model independent. And that's all the rage nowadays. A lot of theoreticians and experimentalists are doing this kind of thing. And so far, the standard model stands a champion, right? All these operators are being constrained, and every measurement is consistent with 0, right? Which pushes this UV cutoff away, right? So talking about future experiments in this case, right? This is the plan for the LHC, right? So this is the, you see, now we're doing this run 3 that should go up to about 350 inverse phantom barns. That's double what we have today in terms of luminosity, right? I hope this does not change because of the explosions of last month, right? But, and then it stops and you go into a high luminosity regime, right? So you do a lot of changes into the accelerator to allow for more luminosity per year, and then the plan is to go about 3,000 inverse phantom barns. Nowadays we have 140, right? So this thing will be way more sensitive to low rare events, right? Events that are controlled by weak couplings, right? And that's the plan. This will happen. Right, so this is the part of the future accelerator program that is happening, right, for sure. And this is the kind of thing that you want to do, right? So again, it's all about the Higgs. So this is all taken before Thiago starts screaming. This is all taken from SNOMED studies, right? So I'm just copying, right? But they expect to get to 0.01% on the measurement of the mass of the Higgs, right? If, sadly, the direct measurement of the Higgs width is way harder than the mass, right? So the precision they expect to get is about 20%. And you see, these are the couplings with the Higgs. And you see all of them, this is just uncertainty expected at the end of this run. So you measure all of those couplings with less than 0.1 uncertainty, right? So that's pretty good, right? Also, that's the big goal for the high luminosity LHC, is to actually measure this guy, right? This is a prediction of the standard model, which we have a predicted value. which is 1 in this plot, right? Because you normalize to 1. And if we see anything different from that, it's physics beyond the standard model, right? So that will be tested in the high luminosity LHC, right? So again, in the high luminosity LHC, you could, in principle, get answers. Now there's this diminishing returns phase, right? Because as you increase luminosity, the significance only increases like the square root of the luminosity, right? So you don't expect big news, but there might be some news. Right? So that's why I won't bet on anything new in the high luminosity LHC, but I might be wrong. Right? Now, really talking about future colliders, including one that is called a future collider, which is a really stupid thing, in my opinion, because eventually they have a logo even, right? When you get there, you have to rename it, I guess. Right? But that's the time frame, right? So this time frame, keep in mind, is from the very first proposal to actually the end of the last run, right? So we are in this phase of theoretical proposals, right? Specifications and all of that for the FCC. This is the size of the thing, and are the energies, right? So you see, with a 10 TeV PP collision, you can probe up to a little higher than 10 TeV, right? Physics. And this is another proposal. Doesn't even have a time frame yet. We're not even sure it works, right? If you can actually accelerate muons and keep them stable long enough to do your experiment. But if it works, it would be really cool because you get to 10 TeV with a much smaller accelerator. This is 10 kilometers. The number is here, but it's too small. Huh? And there's also the Chinese one, right, which is less transparent. It's hard to know what's going on, right? But you see, this is taken from a talk last year, and you see the time frame tells us that should be being constructed already, right? And this is on the talk, and we know it's not being constructed. I also didn't decide the place. Well, maybe they are hiding it, but I don't know. I wouldn't trust too much this time frame, but you never know, right? The Chinese are known for pulling up these civil engineering stunts, right? Where they build, they have a lot of labor, right? And maybe, who knows? That's what they say. Right? And it's very similar in terms of specifications. It's very similar to the lepton version, the electron-positron version of the FCC, right? Similar energies. Essentially, what you're trying to do with this energy is to make a Higgs factory, right? You're colliding very close to the on-shell Higgs mass, so you produce a lot of Higgses and can measure decays of the Higgs in very good precision. And the Chinese also want to go here because then you make a top factory. Right? I don't know if that is also planned. Yeah, that's also for the FCC. It's on the books for the FCC. So again, same phrase I keep repeating, just reinforcement, right? So now the final message, right? What can we take away from all of that? This is especially for the students, right? As a student, what should we do, right? If I like particle physics, what should I do, right? So my point here, right? Again, this is my idea, right? Is that we are looking at a paradigm change in particle physics, right? But it's not a paradigm change of the physics, right? But of the way we do physics, right? Because for the last 100 years almost, right, we have been in a confirmation phase of the standard model, right? We made a few discoveries, right at the start. So we observed kaon strangeness, right? We observed CP violation in KO oscillations. We observed missing energy in beta decays, right? And that allowed us to predict the weak interactions, even if we were way below the scale of the mass of the W and the Z, right? Why was that possible, right? And the reason is that the weak interactions, they break symmetries that are allowed by QCD and QED, that are respected by QCD and QED. And when you do that, right, you have many effects, especially decays, right? Which the leading contribution will be some higher order operator generated by the W's. So you were sensitive to high energy physics, even if you're doing your experiments at very low energies, right? Beta decay is the example, right? You're looking at a weak decay, right? You get information about the W and the Z because of that, right? Which are generating that decay, even before you even close to the mass of the W and the Z. If the beta decay could happen through QCD and QED, we would never notice the weak interaction at all, right? Same for CP violation, the KO oscillation, right? If that was allowed by other parts of the theory, we would never know that the W was contributing to that. Since it was forbidden by all the renormalizable operators that we had, we saw the Fermi interaction, this 4 fermion interaction that is the effective thing generated by the W's, right? And that spoiled us, essentially, right? We worked through this 50, 60, 70-year stretch where we could predict all these particles before they were observed, right? And as the experiments got more and more expensive, we got used to only doing an experiment if you know exactly what you'll find, right? But that's not the usual situation in physics in general, nor for particle physics in any other period of time, right? Sometimes you actually have to do the exploration that will give you hints that allow you to predict what comes next, right? You need experimental input. That's the answer to a question by Pedro last week, right? You could predict just from theory that you have spin 1, spin 0, spin half, 3 halves, and 2 particles. But you couldn't predict how many and what the symmetries they have and what interactions they have. That comes from experiment only, right? And so we need that exploratory phase. And that's what we're entering right now, right? We have no clue what comes next. Literally, I want to make that clear, right? There are many options where we'll see nothing, right? And that's why we have to look everywhere, right? We have to split our efforts and really look for clues and try to find some sign of some new physics somewhere, right? Because we know it's not the end, right? There are many orders of magnitude before you get to the Planck scale. There are many phenomena that are not explained, like concrete observations, neutrino mass, dark matter, etc. Right? And we have to keep looking, right? So if you are an experimentalist now for the students, right, just keep the good work, keep doing experiments, that's good for you. That's what we need, right? And if you are a theoretician, I think that's the main point, right? It was very tempting as a theoretician at this point, especially if you were doing model building or your supervisor did model building for most of his life, to actually continue doing model building and move away from experiments, because you can do model building. If you're not looking at experiments, you can do model building like a king, right? There's no limits to it. Right? But the point is that now we live in a point of time that is not needed anymore. We have a sufficient number of models. Now we have this tool set of models that actually help a lot when you're looking everywhere, because if you don't know what kind of thing could happen, it's very hard to interpret the experiments, right? But we have that, and in building models that are more and more complicated, right? I call them parameter-rich models here, but you understand how bad that is, right? It's not very useful, right? And so the good strategy is actually to get closer to experiments as a theoretician, not farther. I'm not saying you have to become an experimentalist, right? But you have to get closer to experiments, because there's a lot of theoretical work that is needed in the experiments, right? Gaston already mentioned something here when talking about beta decay, right? You need to have some very good calculations of how these double beta decays will happen in nuclei, right? Heavy nuclei. Right? So that's theoretical work. So that's measurement, falls in the measurement proposals that I listed here. You need background estimations, better and better background estimations. You saw from the high luminosity LHC prospects that I showed that even the LHC, a Hadron Collider, is entering what essentially is a precision run now, not a discovery run. Right? They are doing precision measurements now. And that means you need precision backgrounds, you need precision calculations on the theoretical side, right? And that's all needed, and you need theoreticians to do that, right? And also interpreting the data in the most model-detached way you can. Of course, everyone has their favorite model, right? Mine is composite Higgs, but you have to try to detach yourself from that, to have an open view and try to interpret the data as it is and not as you wanted it to be, right? So that's the message, and thanks for the attention.
Questions? Chuck.
I just want to remark that if anybody actually wants to become an experimentalist, we are hiring.
You don't need the mic, right?
Yeah, so I have a question about this vertex that you drew on the board. So I was wondering if this experiment can rule out some BSM predictions, or
Yes, it can.
especially the composite Higgs. I was curious if it can rule it out.
It can push it away, right? So always in both SUSY and composite Higgs model, you have this scale, right? In the case of SUSY, it's essentially the scale of SUSY breaking. In the composite Higgs model is the scale of compositeness, right? So in composite Higgs model, this coupling deviates from the standard model, right? So when you measure it, right? So if you look at this plot, usually in the direction of making it bigger. So if you go close, I went through. Is this one. So as you exclude couplings which are bigger than the standard model, you're pushing the scale of compositeness farther and farther away, right? You're basically saying there's no form factor here, it's just a point, right? But that size of that point can only be pushed away. You can never completely exclude something being composite at, I don't know, the gut scale, right? So you're pushing it away, and then it becomes not a solution to the hierarchy problem, right? The more you push it away, the more fine-tuned it is. But that's essentially what you do with these measurements.
Hi, thanks, Ricardo. About the lepton number violation, I mean, because there are some processes that we just accept they don't exist because we assume that lepton number is conserved, right? So if you allow lepton number violation, what happens to this? I mean, then you need another mechanism to understand that they don't happen, or all the process that where could happen, but if lepton number was not conserved, they could exist, but we don't see because, I don't know, they exist in a very low rate or what?
Yeah. So in the standard model, you don't actually need to impose lepton number conservation at all, right? You just by imposing these symmetries, the ones at the start, right? SU2, SU3, SU2, and U1, and that matter content with the hypercharges that actually feed data, you get lepton number conservation for free. That's why we call it an accidental symmetry. All the operators that could allow it are already forbidden by the other symmetries. But that's the renormalizable part of the standard model. If you go to effective operators, so dimension 5, dimension 6, you just build an effective theory out of the standard model. You put no new particles, and you write all the operators possible for with these particles that you already have and the symmetries you already have. Already at dimension 5, you have the Weinberg operator, this one. Let me find it here, this one, right? And that violates lepton number, right? It allows a Majorana mass for left-handed neutrino, right? And it can annihilate itself. The reason this is not odd for us is that being an effective operator, this violation is suppressed by some UV scale, right? If you assume that this coupling is order 1, and you try to get the masses of the neutrinos that we think, right, milli electron volt scale, then you conclude that this scale should be 10 to the 14th GeV. So really far away, really close out to the gut scale. So that's already, theoreticians go nuts about coincidences, right? Already, a lot of people think, well, it's gut scale that is generating this, right? But then you don't observe lepton number violation because it's only given in the standard model by a higher dimensional operator that is really suppressed.
Is it renormalizable?
No.
No.
No, so then it must be an effective theory, right? This must be a physical cutoff, right? So that's the scale where something
that's
is...
a condition for it to happen, right?
Yeah.
Okay.
Yeah. In the standard model, right? You could always postulate some extension that has lepton number violation. It should always be suppressed because the data is really stringent on that, right? So it's very hard to put lepton number violation to any theory and not be in direct clash with experiments that never observed lepton number violation.
Questions? Yep.
So, hi. Maybe I have a silly question. When you were
I don't
talking
think your
about
mic is on. Or
is
yeah, no.
okay. So when you were talking about when you were explaining the fine tuning and you integrated out the fermion field.
You want the toy model or the...
Yeah, the toy model. Yes. Yes, exactly. So there is a problem if the fermion field has a mass, isn't it? Because
it does have a mass. It's
yeah, it
M.
does in the toy model, but in
oh no,
later,
but this is a toy model.
Exactly.
I'm not assuming these guys have SU2 left, right? So if you didn't have SU2 left symmetry in the standard model, yeah?
So this is a scalar field, and this is to explain the hierarchy problem, right? So
it's an example of a theory that would have it, right?
Exactly, but how this relates to the Higgs field? Because in the standard model, all the fermions are massless. I mean, you could say neutrinos could somehow be, but like...
no, you're saying that I don't have left...
Exactly.
Well, it's very similar, other than this mass, in this case, is generated at the Lagrangian, so it's completely free of the coupling with the scalar. In the standard model, the two things are the same, but you could draw the same diagram for the top, right, with the Higgs after electroweak breaking, right? The top develops a term that looks just like that. The only thing is that the mass for the fermion in that case is not independent from the coupling with the scalar.
Yeah,
but you can do the same calculation.
Okay.
It's not just fermions, right? I could do this loop with W's. I could do this loop with... everything contributes to bring the mass of the scalar up. This is just Wilsonian effective field theory, right? What's really behind this is that the operator for the scalar mass is relevant.
Okay.
Right? As you move away from the UV cutoff, it goes up. Right? And that's general. It doesn't matter. That does not depend on the details of the UV at all.
But if you go to the next slide, you see the fine-tuning comes from the fact that m squared is of the order of y squared big M squared. And if we had no big M squared...
No, but that's what's my question, right? I don't care how big M is, right? I'm just saying, suppose I put all the scales here in a line. My question was, what should I do with the parameters so that I have something that looks like that? Is that possible or not?
But in the Higgs,
can I get a physical mass for the scalar which is much smaller than this thing? That's all. So this is by definition, M is bigger compared to M physical is small compared, because I want to build a theory that is valid up to here. Is that possible? Only if the UV is very specifically tuned. That's all I'm saying, right? In the standard model, I'm assuming I didn't see that fermion. Or I could do the same thing with a vector. It's the same, right? I could do the same thing with a heavier scalar. It would be the same.
But my guess is that we have to assume that the masses don't come from the Higgs mechanism. No, I mean, because the masses in the standard model come from the Higgs interaction, so there's no big M.
No, but the big M here isn't any of the M's in the standard model,
Okay.
right? It's some new physics at some scale, right?
Okay.
This is not a problem at all. There's no hierarchy problem. If you look at this plot here and say, I believe that above the electroweak scale, there are no new scales, none. Nothing, no, there's nothing, right?
But there could be like
Then there's no hierarchy problem. But if anything shows up here, it doesn't matter. I use the fermion for the toy model. Doesn't matter if it's a fermion, a scalar, a boson. If it has a mass, right, if you generate a scale, that scale could even be some dimensional transmutation scale. You could start with a pure young muse up there that gets confined, say, at 10 to the 11. You have glue balls, right? Those glue balls are massive particles that would contribute in a loop to the Higgs.
But
right?
if that mass comes from the
Something.
Higgs mechanism,
No, not necessarily, right?
I-
Not necessarily,
okay, okay,
right?
okay.
That's why I'm saying it's not. It doesn't need to be the mass coming from the Higgs mechanism. Any scale,
Okay.
right, will cause this.
Thanks a lot for the great talk. So I just want to know your opinion. So from the cosmology point of view, it's expected that we get a constraint of the sum of neutrino mass of 20 millielectron volt in about 10 years, right, with the CMB stage 4 experiments. So in your point of view, what does it bring? What does it imply for particle physics?
Sorry, the mass you mentioned for the neutrinos, or
Of the sum of the mass.
well,
yeah.
it puts this excludes the neutrinos essentially, right? So if you're talking that, sorry, I didn't understand everything you said. You say that constraint is for dark matter or for the mass of the neutrinos?
For the mass of neutrinos. Yeah.
For the mass of the neutrinos. Okay, that puts this constraint on the Yukawa coupling, right? So this plot essentially, let me go back to it. So this point, right? So you know they are not here, right? They should be somewhere down below. This dashed line here is what you say, is the sum of all the masses of the neutrinos, right? It should not be bigger than this. Right? And that is used as motivation to say that this bad solution is very improbable, right? Because this gap is read by the theoreticians as there is some mechanism generating the mass for these guys, which is the Higgs, right? And there should be a completely different mechanism generating the rest, because you see they are very different. Another argument in that direction is this mixing pattern that I commented at the end, right? This one. So the mixing for neutrinos is very different than the mixing for quarks. All of these are used as clues to say, well, the neutrino masses are very different from the standard model, right? Again, hand waving, right? So if they are generated by the interaction with the Higgs, then you get into that situation where it's tiny, tiny coupling, and will be very hard to ever prove that the neutrinos are just Dirac particles. Right? That's very hard to prove experimentally.
So if we don't have other questions, I have one final question and a comment. Basically that it's very difficult to find something when you don't know what you're looking for. So if you were a student today and beginning your PhD, would you go, what's your take? Would you go to neutrino physics, to the electroweak sector, to QCD?
If I had to start anew, you mean?
Yeah. Today. Doing something else? No, this is
today,
not an option
probably neutrino physics, because there's a lot of really near-term experiments about to happen, right? So it's very good to get a job, especially when you're a student and you get higher, right? There will be more money in that than in the other. It's not because I believe there's more chance for new physics there, right? It's because it's from the point of view of what will be more active in the near term, I would say neutrino.
Even for theoreticians?
Even for theoreticians. Right? You need a lot of theoreticians inside those experiments, right? Yeah.
Okay, thank you. So any other question? So let's thank again this beautiful lecture.